Good morning, everybody, and welcome to the CEIA Maths tutorials. Today we've got Trigonometry 1 and 2, and we're delighted to have Ed Collins and Frank O'Keefe, who are both going to take this morning's tutorial and hopefully enlighten you a little bit. Okay, so to take the first part of the tutorial, we've got Edmund Collins, who you've already met in a tutorial 3 weeks ago now. So if I could hand over to you, so Ed, to take the floor. Okay.
Thank you, Eamon, for the introduction. My name is Ed Collins. I'm a chartered mechanical engineer. As Eamon said, I presented to you in the first tutorial on indices and logs, and I'm very pleased to be presenting this morning on trigonometry. So I'll be taking the first part of the tutorial, Trigonometry 1, and then Frank will take over with the second part, and Frank will be concentrating a lot on trigonometry, trigonometric identities. So some of the material that we're covering this morning is in your log tables. Certainly a lot of the identities are in there, the sine, cosine, tan, and so on. But it's important that you're very familiar with the use of these techniques. And Jerry last week in his tutorial mentioned the techniques that we use in mathematics, and trigonometry is one of the key techniques that we use, along with calculus and other techniques. But in preparing for the tutorial, I was looking back on, I suppose, the roots of trigonometry, and certainly it was quite clear that geometry is a very close relative to trigonometry. So it's important that you're comfortable working with triangles. You understand the key concepts around triangles. Obviously, we've the likes of Pythagoras' theorem, so you should be very familiar with that. But are you familiar with equilateral triangles? What does an equilateral triangle mean in terms of the angles, the three angles in the triangle, isosceles triangles, and so on? So if you feel that you're not as comfortable with geometry as you would like to be, then I would suggest going on to some of the websites. We've talked about this in some of the other tutorials. One I'm quite happy with and in favour would be the Khan Academy website, and that covers not only mathematics but physics, chemistry, and so on. And they have some good tutorials on geometry there. For example, the proof that the three angles in a triangle equals 180 degrees. And when you look at the proofs and go through them, it helps with your understanding, and you become more comfortable then when you're doing problems, when you understand why the three angles in any triangle equals 180 degrees. Then that's important when you're problem solving and in trigonometry. So certainly geometry is a key part of the understanding of trigonometry. So what are the applications of trigonometry? Well, they vary quite a bit. So we start with the first photo there in the top left hand side. You can see a photo from the International Space Station. It's Canadarm2. The first Canadarm was developed for the space shuttle. It's used to deploy satellites in space, also for spacewalks and so on. So you see the astronaut there on the Canadarm2 on a spacewalk. So there's various joints on the arm and so on. So certainly the engineers and scientists working on the development of the Canadarm would have used trigonometry, calculating angles and so on. And there's actually a good question in one of the past Leaving Cert papers in relation to a robotic arm, and it will cover some of the work that the engineers would have done on Canadarm. Then if we go to the top right-hand photo there, we see trigonometry being used in astronomy, in parallax, to determine distance of certain stars and so on. So again, it comes up quite a bit in astronomy. And then going to the bottom left-hand corner, you see there it's used in aeronautical engineering, glide paths for a glider. That should be a very routine type of calculation in aeronautical engineering, but very important. And I suppose trigonometry is used extensively in applied maths and in physics in forces. So when you're actually working forces and you're looking at the horizontal and vertical aspect of forces, then trigonometry comes in quite a bit there. Now, it's also used extensively in navigation. There's a particular form of trigonometry which we won't be covering here, but if any of you do end up in the maritime sphere, then certainly this form of trigonometry will come into your studies. I suppose I've used trigonometry to some degree in my career, but I say that I've a yacht, and I've done yacht master courses, and I've used trigonometry extensively in navigation. So it certainly comes in there quite a bit. So here's the agenda for this morning's tutorial. I'm going to cover measurement of angles, the trigonometric ratios. Again, these are in your log tables, but I want to go through them in a bit of detail. I suppose just as an aside, it's important that you don't have to go to your log tables for everything. It could cost you a bit of time doing the exam. So it's good if you can bypass the log tables if you're happy enough with the concepts. Then I'm going to go on to reference angles, and then the signs of sine, cosine, and tangent in 4 quadrants in the unit circle. That's quite important. Going to look at the sine rule and the cosine rule, and these are used a lot in problem solving. And then I'll go on then and do some exam questions where you'll see the application of a lot of what we would have done previously in the tutorial. So hopefully by the end of this, you'll have a better understanding of the technique. So starting off with the measurement of angles, well, if we want to calculate an arc length S there in the circle, so what we need to envisage here is the radius of the circle starting at the x-axis and then rotating an angle theta a certain amount. So what is the arc length due to that rotation? The arc length is given as r times theta. Now, you all know that the circumference of a circle is 2 pi r. So therefore, theta in this case must be 2 pi, but it's 2 pi radians. So therefore, 2 pi radians equals 360 degrees because we rotate it around 360 degrees. And just to see the convention that we'll be using this morning in terms of reference angles and so on, and also Frank will be using the same convention, is an anti-clockwise rotation. So it's a bit different. For example, on a compass, we tend to go east, north, east, south, west, and so on, and that would go clockwise. But in all of the work we'll be doing this morning, we'll be working in an anti-clockwise direction. So that's why I've shown theta there, moving in an anti-clockwise direction. So 360 degrees equals 2 pi radians. Therefore, 1 degree equals pi over 180 degrees radians, and 1 radian equals 57.296 degrees to 3 decimal places. Now, this again is in your log tables, but it is important to understand the concept of radians versus degrees, and to be able to work to switch from degrees to radians and vice versa. In some of the questions, the information may be given in radians, or you may be asked to give your answer in radians. So you have to be quite comfortable with working between the two. Now, again, this is in your log tables, but these are some of the key angles, if you like, shown in degrees and radians. So 0 obviously is 0 degrees is 0 radians, 45 degrees is pi over 4, 90 degrees pi over 2, 180 degrees pi, 270 degrees 3 pi over 2, and 360 degrees 2 pi. So you shouldn't need to be going to your log tables to say, well, you know what, if you're asked for an answer in radians and you're getting pi, you should know well, that's 180 degrees. Okay. Now we're going to move on to the trigonometric ratios. You should be very familiar with these, well, the first 3 anyway, because they come up quite a bit in questions, and they are used extensively in problem solving in trigonometry. So I'm going to use the triangle here at the top of the slide, and I've used the convention that the angle is shown in uppercase there, B, and the line opposite the angle is shown in lowercase b, and similarly for the adjacent and the hypotenuse. Now, it's very important to remember that these trigonometric ratios are only used for right angle triangles. So that's very important. If you have any other sort of triangle, you cannot use these. You use other techniques. So in the case of sine, it's opposite over the hypotenuse, so it's b over c, and we can use a little memory jogger here. So we call this so, and obviously we've ka and toa. So saka toa is one way of remembering this to help you. So SOH, so it's the sine is the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse, so that's a over c, and that's ka, so cosine c, a adjacent, h hypotenuse. Tangent then is opposite over adjacent, so that's b over a, and that's toa, toa. And actually, if you look at it, the tangent is also the sine over the cosine. So if you work that out, put the sine over the cosine, well then that'll be the tangent. So that's something that may come in useful in problem solving. So they're the first 3, quite important, and we will be using them later on in problem solving. The next 3 are the cosecant, which is basically 1 over sine, or c over b. So it's the hypotenuse over the opposites. So it can be a bit confusing when you look at cosecant. You may think that it's 1 over the cosine, but it's 1 over the sine. And one way I find to help remember that is if you go to the third letter, co-sequence COS, then that's sine, so 1 over sine, so that can help, but that could be a point of confusion there. The secant of an angle is the hypotenuse over the adjacent. In the case of our triangle here, it's C over A, and it's 1 over the cosine. Again, the third letter there is C, so that could help you just remember that it's 1 over the cosine. And then finally, the cotangent is easy enough. We know it's 1 over the tangent, and that's just the adjacent over the opposite. So A over B. But just going back to the sine and the cosine, if we square the sine, so again from the indices we would have done a few weeks ago, we know that b over c squared is b squared over c squared, and we squared the cosine, that would be a squared over c squared, and if we add those two together, we have a squared plus b squared over c squared. Now we know from the theorem of Pythagoras that a squared plus b squared equals c squared. So then we end up with c squared over c squared, which is 1. And Frank's going to talk quite a bit about this in identities, that the sine squared plus the cosine squared equals 1. And that's the proof of it. So it just helps. If you can see where these things come from, I find that it helps with your understanding, and you become more comfortable using that. Just knowing where it comes from, the understanding does help. So sine squared b plus cosine squared b equals 1. Now, a little question for you. It's quite simple, really. You've probably come across this before, but just helps to reaffirm some of the concepts that we've talked about in the last few slides. So here we have a right angle triangle, and you see the little square in the bottom is used to show that it is a right angle triangle. In the case of a right angled triangle like this, one angle is obviously going to be 90 degrees, but the two sides are equal here, and because the two sides are equal, then the angles opposite those sides are going to be equal. And we also know then that the three angles must add up to 180 degrees. Therefore, we can determine that each of those angles is going to be 45 degrees. We know from the theorem Pythagoras that squaring the hypotenuse, you sum the squares on the two sides. So the length of that is going to be root 2. So using all that information that we've given you there, can you determine the sine, cosine, and tangent of a 45-degree angle in third form? So I'll just give you a minute there to work on that little problem. Straightforward enough, really. So remember, think of SOHCAHTOA as you're doing this problem. So SOHCA, sine, opposite over hypotenuse, cosine, adjacent over hypotenuse, and tan, opposite over adjacent. Okay. So here's the result. The sine is the opposite over the hypotenuse, so it's 1 over root 2. Sine of 45 degrees. The cosine of 45 degrees is the adjacent over the hypotenuse, and that's also equal to 1 over root 2. So they're both the same. And the tan of 45 degrees is equal to 1. So again, in the log tables, they have sine, cosine, and tan for what we call the standard angles, the 90 degrees, the 0, the 45 degrees, the 30 and the 60 and so on. But this one you should know off by heart, and some of the others if you can learn them off as well, but it would help. But certainly this one is very easy to remember. So hopefully you found that a bit of a help to apply the principles of SOHCAHTOA. Now we're going to move along to reference angles. Again, as I mentioned earlier, we're going to be moving in an anti-clockwise direction. So basically, reference angles are used to determine the sine, cosine, and tangent of angles which are greater than 90 degrees. Because we can have a problem here. We're talking about an angle of 135 degrees. So what does that mean when we're dealing with an angle, an obtuse angle? Up to now, we've been dealing with acute angles less than 90 degrees. In the first case, if an angle is less than 90 degrees, then we don't need a reference angle. Basically, the reference angle is the angle. So that's straightforward enough. So we would work as we have worked in the previous slides. So no problem there. However, if we have an angle that's greater than 90 degrees, less than 180 degrees, then in this case, we trap the reference angle. So you see we've rotated the angle A from the first quadrant into the second quadrant. We've dropped a line from the circumference down to the x-axis, and we've trapped an angle, or that's the reference angle. So the reference angle in this case is 180 degrees minus A. So if we were to rotate 135 degrees, then the reference angle would be 45 degrees, 180 minus 135. And the reference angle in this case in the second quadrant. So moving along, we rotate again. So we've an angle that's greater than 180 degrees, but less than 270 degrees. Then the reference angle in this case is the angle minus 180 degrees. And again, we're dropping, or we're taking a line from the circumference up to the x-axis, trap the reference angle there in the third quadrant. Finally, then, if we have an angle which is greater than 270 degrees and less than 360 degrees, then the reference angle in this case is 360 degrees minus the angle A there that we traced out. And in this case, we're again taking a line from the circumference up to the x-axis, trapping the reference angle there, and the reference angle is in the fourth quadrant. But what about the signs of sine, cosine, and tan in different quadrants? Yes, we've calculated what the we've determined what the angle would be, but now how do we calculate the sine, cosine, and tangent of those reference angles? So we can use the unit circle to do this. Unit circle is very good because the radius is 1, and it's easy then to work out what sine, cosine, and tan is going to be at different angles. So it's a good technique to use. So in this case, the radius is 1. So let's take the first quadrant again. So everything is going to be as we would have seen in original SOHCAHTOA examples. That is, the sine of the angle in the first quadrant is positive, the cosine of the angle in the first quadrant is positive, and the tangent of an angle in the first quadrant is positive. However, as we move either to 0 angle or up to 90, things happen there. So if we're on the line, so if we're at 0, then you see that the sine of an angle is as we've seen previously, is the opposite over the hypotenuse. As we move back, if you could just envisage that radius moving back down to sit back down onto the x-axis, then the the vertical component, if you like, of that triangle is getting smaller and smaller. It's actually going to 0. So therefore, the sine of 0 degrees is 0. So it can help with that understanding by looking at this and visualizing the radius moving. And likewise, as the radius moves down to the x-axis, the adjacent will actually will sit on top of the hypotenuse. So therefore, that's why the cosine is 1. The tangent is 0, for the similar reason that the sine is 0. That's at 0 degrees. However, if we move up to 90 degrees, it's reversed in relation to sine and cosine. So the vertical component of the triangle is sitting on top of the radius there at the hypotenuse. And therefore the sine is 1 at 90 degrees, but the cosine goes to 0. Something happens, the tangent, it's undefined, it actually goes to infinity, because what's happening there is we're dividing by 0. And as you know, that as you start dividing by 0, funny things happen. You're basically going towards infinity. And we'll see that later in the plots of sine and cosine x and tan x, what's happening there. That's the first quadrant situation. The second quadrant situation, the sine of an angle in the second quadrant is positive, because you see the vertical component is coming from the positive y-axis, so that's positive. But the cosine is negative, because the horizontal part of the triangle there, the adjacent part, is on the negative part of the x-axis, so that's negative. And likewise, then the tangent is going to be negative. But what happens here in relation to 180 degrees? Well, the sine goes to 0, the cosine goes to -1, and the tangent goes to 0. We'll see this again, maybe a bit easier when we look at the graph. So we're into the third quadrant now. So what's happening? Our sines here, the sine of sine and cosine and tangent. Well, the sine of the angle is going negative, because our component, our opposite is on the negative y-axis. The cosine is also negative, but the tangent in this case is positive, because we have a negative over a negative, and so we have a positive. So therefore, as we go towards 270 degrees at the 270 degree angle, the sine is -1, the cosine is 0, and the tangent again is undefined, because we're dividing by 0. So finally, in the fourth quadrant, the sine is negative. Again, we're on the negative part of the y-axis. The cosine is positive, because we're back. The adjacent is back onto the positive part of the x-axis, and then the tangent will be negative. For an angle of 360 degrees, the sine is 0, cosine is 1, and the tangent is 0. So this can be summed up neatly in this slide here, and to help you remember the rules around the sine of the sine, cosine, and tan in the different quadrants. You can think in terms of this axe, what's called axe. So now this works in the ACTS, works in a clockwise direction, starting from the first quadrant. So you go from the first quadrant to the fourth, to the third, and into the second. So there in the first quadrant, we can see that they're all positive: sine, cosine, and tan. In the fourth quadrant, we see that it's only cos is the cosine is positive. In the third quadrant, we see that only the tan is positive, and then in the second quadrant, we see that it's only the sine is positive. So to remember that, AX, ACTS, again, pretty sure this may be in your log tables, but if you can remember this and you don't have to go to the log tables, you'll save some precious minutes during the exam by just being able to remember that. So AX, ACTS in a clockwise direction. Now, this is a plot of sine x and cosine x, and it's actually giving us a lot of the information that we would have looked at on the slides in relation to the unit circle. I used Excel to plot this out, and if some of you have access to Excel, it might be a nice little exercise to do. The plot came out quite well. I'm plotting the angles in radians there, as you see. So starting at 0, and then I'm showing pi over 2 pi, 3 pi over 2, 2 pi, and then I just go to 3 pi and so on. But what's interesting here as well, that I've also plotted negative angles. So I've plotted minus pi over 2, minus 3 pi over 2, and minus 2 pi. So the negative angle, it's basically an angle going in the clockwise direction. So if we were to go back to our previous slide, looked at the first quadrant, but if we rotate it in an anti-clockwise direction, well, that's a negative angle. So I suppose the first thing to notice here is that it's a repeating cycle here. So it's a wavelength really. We start with 0 in the case of sine, and we go to 2 pi, and then the cycle starts again, 2 pi to 4 pi, and so on, goes on and on. Sine waves happen naturally in nature. For example, the tides follow this wave pattern. Pendulums follow this wave pattern sign. So it is used a lot in physics and so on, and in electronics. So sine wave is a very important, or the sine function is very important. But if you look at the cosine, then it has the exact same appearance as the sine, except at the angle 0 degrees or 0 radians, the cosine is 1, whereas the sine is 0. But it's 90 degrees out of phase, and it's actually interesting. Just think about that. When you're looking at the identities that Frank is going to go through. So that's a key thing to think about. Sorry, Eamon, can you just confirm, is that clear, the chart there?
Yes, it's fine, Ed.
Thanks, Eamon. So just bear that in mind, that they are 90 degrees out of phase, and they do follow the same pattern. So what else can we say here? Well, if you look at the cosine graph, and you look at the value for pi over 2 and minus pi over 2, you will actually see that they're the same. So again, think about that when Frank is going through the trigonometric identities, because the cosine is what's called an even function. But if you look at the sine of pi over 2 is 1, the sine of minus pi over 2 is minus 1. Sine is an odd function, because the sine of a positive and negative angle will have different signs. So that's something you can tell from this graph. Also, it's interesting to note where the two graphs are intersecting. Sorry. So our first intersection there, I haven't actually shown the point, but down on the x-axis, but it is pi over 4. So it's 45 degrees. And the next point of intersection on the positive part there is 135 degrees. So you can see the intersections, and this lines up with what we would have looked at earlier, that the value of the sine and cosine of 45 degrees is the same. So a lot can be read from looking at sine and cosine on a graph like this together. And I would recommend you doing that, plot it out even by hand on a piece of graph paper, or else do it on Excel, or there's some apps I'm sure that you could use online to do it. But it will help your understanding about how sine and cosine behave. Now, this is an interesting graph too. I didn't generate this. It came from this website, calculatorsoup.com. I don't know a whole lot about it, but they certainly had a very good graph for tan x. And you can see that this is a repeating process here in terms of the graph going through 0 there. So we can see again from the work we did on the unit circle, if we take the positive part, pi over 2 radians, that it goes to infinity. It's asymptotic there. It comes back from infinity there, goes up towards pi. It's 0 at pi radians, or 180 degrees, and then moves up towards infinity at 3 pi over 2, and so on. And it repeats itself. And likewise for minus pi, it's 0, minus 2 pi, it's 0. So again, looking at this graph can help your understanding of how the tangent behaves as you're moving from 0 to pi to 2 pi. But it is an interesting, very interesting graph, seeing how pi performs. So now we've another little question here, again based on the work that we've done with reference angles and sines and so on. Find the sine, cosine, and tangent of 135 degrees. So I'll just give you a bit of time to think about that. So 135 degrees, I'll give you a hint anyway. We're in the second quadrant there. Is 180 degrees minus the angle. So just think about that, and then think about the axis as well, the ACTS, and going from the first to the fourth and so on around clockwise. just in relation to the problem we were looking at, the sine, cosine, and tangent of 135 degrees, the reference angle is in the second quadrant. So that's 180 degrees minus 135 degrees, which is 45 degrees. The sine in the second quadrant is positive. The cosine and tangent in the second quadrant is negative. So the sine of 45 degrees is 1 over root 2, as we saw earlier. The cosine of 45 degrees in the second quadrant will be negative, so that's minus 1 over root 2. And the tangent 45 degrees in the second quadrant will be negative, that's minus 1. So the sine rule used extensively in problem solving, but is used for non-right angle triangles. So again, you'll see the same method of denoting angles and lines that we used earlier. So large A is opposite line small a. So in the case of the sine rule, A over sine A equals B over sine B equals C over sine C, or you can invert it to sine A over A equals sine B over B equals sine C over C. As I said earlier, it's used for non-right angle triangles. And it's used when you know the length of one side and the angle opposite. That's important. So if you're given a length in a problem, but you're also given the angle opposite that length, then you will use the sine rule, and hopefully we'll be able to see that a little later on. Now, the next important rule we use in problem solving trigonometry is the cosine rule. Again, same method of denoting angles and lines here. And there's a number of versions here in relation to this triangle. So the cosine rule says that a squared equals b squared plus c squared minus bc, the cosine of a. But you can also write it as b squared equals c squared plus a squared minus 2ca, the cosine of b. Or you can write it as c squared equals a squared plus b squared minus 2ab, the cosine of c. So one way to remember this is, when you look at the three versions of it there, is that the angle will be the one associated with the left-hand side of the equation, if you like. So in the case of a squared, then we're looking at cos a, and the other two lines are on the right-hand side, and the minus 2b is one multiplied by the other. So that is a way to remember it. Again, it's in your log tables, but it is important to know when to use it and how to use it. It's used when you know the length of sides of a triangle, but not the angles opposite them. So it's different to the sine rule. So they each have their place, and it should be evident when you're looking at a problem which one to use. So we'll now have a look at some problems, and I'm going to switch on to the whiteboard. Is that visible, Eamon? Sorry, Eamon. Sorry, Eamon, can you see the whiteboard?
No, Ed, I'm just seeing the PowerPoint still.
Okay, sorry, I'll just move it there. Can you see it there now?
Yes, all good now.
Very good, thank you. Okay, this is question 7 of paper 2 from 2016. Looks a bit daunting at first, but it was quite an easy question in the sense that it gave some of the answers, and one part of the one answer built or one part of the question built on the previous part, so on. So if you got settled into the question, it wasn't too bad. But we'll read it there. So a glass roof lantern in the shape of a pyramid has a rectangular base, C, D, E, F. So we were talking last night about this when preparing for the tutorial, the importance of reading the question thoroughly. Spend your time reading the question and underline things, highlight things, just to make sure that that you understand all the information that's been given and what's been asked. So the apex of this pyramid is at B, and the vertical height of the pyramid is shown as AB. Now, some of you who do engineering drawing, technical drawing, whatever, would be familiar with the way this is drawn. So the dotted lines would indicate hidden lines. So if we were looking down on this pyramid, you wouldn't actually see these lines, but they are given so that you understand how the pyramid is constructed. So vertical line of the pyramid is AB, where A is the point of intersection of the diagonals of the base as shown in the diagram. Now this is going to be very important in the first part of the problem solving. So we've got two diagonals intersecting. Basically the diagonal lines are going to be divided in half there. That's going to be used in the first part of the question. So also then is shown CD equals 2.5 meters and CF equals 3 meters. So that's all the information we're given there. But by implication, EF is rectangular base. EF is going to be 2.5 meters, and ED is going to be 3 meters, or DE is going to be 3 meters. So that's important. So the first part of the question, show that AC equals 1.95 meters, correct to 2 decimal places. So again, the importance of reading exactly what's been asked. So we need to work to 2 decimal places. So so we're looking for AC, but if we were to start writing in a bit more information here, so we know that DE is 3 meters. So we actually have a triangle here that we can work with. So we're always looking for triangles. So this is a right angle triangle here, and we have 2.5 meters with 3 meters. So we can use Pythagoras theorem here to calculate out CE. So using Pythagoras theorem, write this out. CE squared equals CD squared plus DE squared. So substituting for CD squared, well, that'll be 2.5 squared plus DE squared will be 3 squared. So that's going to be 6.25 plus 9, and that equals 15.25. So C is going to be the square root of that, which equals 3.90. But we're looking for AC, but because we know that AC is half of CE, therefore AC will be CE divided by 2. That's 3.9 divided by 2, and that equals 1.95 meters to 2 decimal places. So don't forget to add in the meters as well. The examiner may be kind to you, may not take off any marks if you didn't put in the M there to denote meters. And likewise, if you left it at, for example, 1.9525, he or she may not take off marks, but you've been asked to show that AC equals 1.95 meters. So you should write that in. So that's the first part of the question. So the key there was identifying the triangle that we wanted to use to calculate out AC, which was half of EC. So the next part of the question, we're given a bit more information here. The angle of elevation of B from C is 50 degrees. So in other words, BCA equals 50 degrees. Show that AB equals 2.3 meters, correct to 1 decimal place. So again, we should mark out the triangle we're interested in. So this triangle here, so that did it well for me there, marking it out. And we've been told here that this is 50 degrees. So we've already calculated out what AC is. So we've got that. We know that that's 1.95 there. We want to determine what AB is going to be. So in this case, we're going to use TOA, so that's the tan. So the tan of 50 degrees equals AB over AC. That equals AB, over 1.95. So working that out, AB equals 1.95 multiplied by the tan of 50 degrees. And that equals 2.324. But again, we're asked to give the answer correct to one decimal place. So AB equals 2.3 meters. So that's the second part of the question done there, using the tan. So the third part of the question is quite easy, because we have we're to find BC correct to the nearest meter, but we already have two sides of the right angle triangle. We have AC and we have AB. So BC is we're just going to use Pythagoras' theorem there. So very easy part of the question there. So in this case, BC squared equals AC squared plus AB squared. That equals 1.95 squared plus 2.3 squared. That comes out at 9.09. BC then will be the square root of that, and that equals 3.015. But we've been asked to give our answer to the nearest meter, so BC equals 3 meters. So quite an easy part, that. So moving on to the next part. Find the angle BCD correct to the nearest degree. So I've gone on to another screen here, but I've drawn out the triangle, the isosceles triangle that we're going to be working with here. So we know two sides are 3 meters and the base is 2.5 meters. Now there's two ways of approaching this. We could use the cosine rule, but we could also do it somewhat simpler by dropping a line down here and creating a right angle triangle with a base half of 2.5, 1.25. So then we could, using our cosine formula, we can say that the cosine is 1.25 over the hypotenuse over 3. So that is the easiest way of doing this. So because of BCD equals 1.25 over 3, that equals 0.42. And then looking that up, we see that BCD equals 65 degrees to the nearest degree. So that was a simpler way of doing that problem. Say the cosine rule would have involved a lot more calculations. So you will find that there may be several ways of solving a problem, and you won't lose or gain any marks by using a particular method. In the marking schemes, they'll identify the two methods that can be used. And then finally, I'm going to leave this one for you to do as a follow-up to the tutorial. So again, we're using all the information that we would have obtained doing the previous part of the question. So find the area of glass required to glaze all 4 triangular sides of the pyramid, and give your answer correct to the nearest square or meter squared. So there's 4, as they say, there are 4 triangles. It's interesting that when you draw out the triangles, they're 2 of each type. One is an equilateral triangle, which has equal sides. If they have equal sides, then again from geometry, the angles will all be equal inside the triangle. They'll all add up to 180 degrees. So they're going to be each 60 degrees. So that's the first triangle. The second triangle is an isosceles triangle, and you can use a very important, I just write it out here, a very important formula, again in your log tables, but there's 2 ways of calculating the area of a triangle. Half the base but the perpendicular height. But also you have this formula here, so it's half. So if we have a situation like this, where we have AB and theta there, it's half AB sine theta. That's very important. So in the case of this second triangle here, we can use that. So we can say half by 3 by 2.5 by the sine of 65. So that can be used in that case in the second triangle. So that's a very important formula to be aware of. So you can work away on this, and I'll give you the answer so that you'll have the answer to make sure that it's correct. It's 15 square meters. So please try that just to finalize the problem. It's important with technique such as trigonometry is to practice. There's all the past papers are available. Just work your way through them. Model answers are available, but I would suggest give it time. If you're really stuck, you can go in to help your understanding. But try and work it out yourself. So there is one other question I was going to go through, but time is moving on. I'm conscious that Frank has a lot to cover and we want to just take a 10-minute break. But it is a question that I would recommend you try. So it's a fairly recent question. It's from 2019, and it's quite a straightforward question, but it does involve identifying different triangles, a bit like what we were doing there in the last question. So it's to do with a helicopter pad and basically you start off the first part of it, the SG, you're going to be using the cosine rule to solve that part. In part B there, you're going to be using the sine rule, and then in part C, you're going to be using the formula for a triangle. So I'll just bring it up here. Similar to what we would have used in the last question. So that's half of AB by sine theta. And then you move on to use other formula, the area of a triangle using the base by the perpendicular height. So I would strongly advise to actually try this question as soon as you can, based on the work we've done in this tutorial, because it will help reinforce the concepts and principles. So I hope you found this part of the tutorial useful, and apologies again for the loss of the internet, but I hope it didn't take away from the tutorial. We're going to take a 10-minute break, but I'll pass over to Eamon there, and I'll see you hopefully in some other tutorials. And I wish you all the best again with your studies, and hopefully you're getting some help from these tutorials. Take care now. Bye.
Thank you, Ed, for that tutorial and for dealing with the internet problems we've been having. So if we could just have a short break at the moment. It's just past 11:22. So if we could be back here to start the second part of the tutorial at 11:30, please. Okay, so see you back here in just a few minutes. Okay, welcome back, everybody. And thanks again to Ed Collins for delivering the first part of the Trigonometry 1 and 2 tutorial. Up next, we've got Frank O'Keefe to go through the second part of this tutorial. So if you're ready to go there, Frank, I'll hand over to you.
Thanks, Eamon. I'll just share my screen now. Okay, hello everybody. Sorry about the delay there. My name is Frank O'Keefe. I'm a telecoms engineer. I'll be going through Trigonometry 2 with you. We've lost a little bit of time, so I'm going to go through this quite fast. I apologize if it's too fast. I think Eamon will be making the recording available later anyway, so you can do a slow motion replay if you need to. With that said, let's get started. Right, so we're going to cover the remainder of the trigonometry course today. So we'll start with the functions of negative and complementary angles, and then the inverse trig functions. And then we're going to go through derivations and uses of the various formulae that you'll find. There are 2 pages in the log tables that you should familiarize yourselves with. Because they're in the log tables, you don't necessarily need to memorize all of those formulae, but you do need to be aware of the fact that they're there and how to use them. And in some cases, you need to be able to derive them. So we'll go through the derivation of several of those. And they can be broken down into the compound angle formulae, double and half angle formulae, and formula using or involve transitioning sums and differences to products and vice versa. Then we'll work through some examples, primarily trigonometric identities, which are common questions asked in the exam. We'll look at some other exam questions as well if you have time at the end. Right. So let's start with the negative angle formulas. First, let's recap on the stuff that Ed has already covered. If you look at a positive angle, and by convention, a positive angle is one that is rotated anti-clockwise from the x-axis. So that brings it above the x-axis. If we take an angle A, it will describe in the unit circle, it'll describe a triangle with some opposite line of length h and an adjacent w. So by definition, since the hypotenuse is 1, the sine of this angle A is h and the cosine is w. And that intercept between the line of the angle with respect to the x-axis and the unit circle itself, that intercept point has coordinates that are cosine A and sine A, in this case, WH. So to reiterate, the cosine of A is W, the sine of A is H. Now if we introduce a negative angle, which by convention is rotated clockwise from the x-axis, bringing it below the x-axis. And if we keep this magnitude of that angle the same, so we can say it's minus A. Again, the intercept point out here is the cosine of minus A and sine of minus A. But in this case, it's W and minus H. So the x coordinate stays at W, the cosine stays at W, but the y coordinate, the sine, has flipped in sine to be minus H. And by comparison, you can then see that the cosine of minus A is still W, so it's the same as the cosine of A, whereas the sine of minus A is now minus H, which is minus the sine of A. So just put those two identities in a box there because they are to be remembered. Right, moving on. You can work out tan of minus A the same way. Or you can use the definition that tan is sine over cosine. And then you see that the sine of minus A needs to be replaced by minus sine of A. Cosine of minus A is unchanged at cosine of A. So you get minus the sine over the cosine of the original angle. So that's minus the tan of the original angle. So for convenience, I've collected those three identities down here. Now let's talk about complementary angles. Complementary angles are defined to be two angles which add up to 90 degrees. So inside a right angle triangle, the two acute angles, A and B in this case, are complementary angles. And you can quickly show, because there's a 90-degree angle in there, and all three angles add up to 180 degrees, that those two complementary angles add up to 90. And so you can say that one is 90 degrees minus the other. So B is 90 degrees minus A, or alternatively, A is 90 degrees minus B. Now, I've drawn it here with the sine of A, the opposite length here I've put in as Y, the adjacent is X. So the sine of A is Y over the hypotenuse Z, and the cosine of A is X over the sine of Z. However, if you look at the complementary angle B, its opposite line is X, so its sine is X over Z, and its cosine is the adjacent over the hypotenuse, which is Y over Z. So it's the opposite of what you were seeing for angle A. And there, you can see then sine of A is Y over Z, the cosine of B is Y over Z. So the sine of A is equal to the cosine of B, and vice versa. And generally speaking, sine of 90 degrees minus an angle is the cosine of that angle. The cosine of 90 degrees minus an angle is the sine of the angle. Now, less commonly used is the tan of 90 degrees minus a, but you'll see that since you're replacing y over x by x over y, you get that the tan of 90 degrees minus a is 1 over the tan of a. And again, I've collected those three results in a box down here because they are also to be remembered. Okay, inverse trigonometric functions. The normal trigonometric functions, sine, cos, and tan, give you the ratio, whether it's opposite over hypotenuse or adjacent over hypotenuse or opposite or over adjacent. It gives you one of those ratios for a given angle. So you put an angle into the function, you get the ratio out. Inverting that process, which is taking the inverse sine, you put that ratio into the function, the ratio x, and it returns the angle, that a in this case, which would produce that ratio, that sine. So you're asking the question, when you say a equals inverse sine x, you're asking the question, what angle a has this sine value x? And the same applies to cosine, inverse cosine, and inverse tan. Now, the problem is that usually, nearly always, you have more than one angle that will produce a given sine or cosine or tan. And you need some way of handling that problem. So as an example, if you want to get the inverse sine of minus 0.5, which is saying what angle has a sine equal to minus 0.5. If you look at the unit circle and you look at what angle has a sine of minus 0.5, that's looking at what angle intercepts the circle at a y value of minus 0.5. So that's this line I've drawn here, the dotted line below the x-axis, where y is minus 0.5. And you see that one angle, which is minus 30 degrees in this case, would produce an intercept on that line. So you can say that the sine of minus 30 is minus 0.5. By the way, you could always also call this angle plus 330. You could imagine it as being an angle around that way. So plus 330 is equivalent to minus 30, and that's a general rule that we'll see later. But anyway, this is one of the solutions of the problem, what angle has a sine of minus 0.5. But you can immediately see that there's another angle which intercepts at this other point over here that has the same sine. And in this case, it's an angle of minus 150. So by inspection, you'll see that, generally speaking, inverse sine, inverse cosine, and inverse tan, which you have to be more careful with, have two solutions. There's an extreme case where you're getting the inverse sine of plus 1 or minus 1, and then this line would be a tangent up on top or on the bottom. And then there's only a single solution. But generally speaking, there are two solutions. And those solutions are in different quadrants. So if we look at that in a different way, if we look at the plot of the sine function, and the sine function extends beyond 360 degrees. So if I can just go back a second, you can imagine angles where you rotate around to, say, in this case, it's plus 210 degrees, being the same as 150. But you could continue to rotate around through 360 and add on another total of 360 to give you 410 degrees in this case. Sorry, 510 degrees. And you get back to where you were. And that's what this graph here is showing. The sine function, it goes positive, it goes back to 0 at 180 degrees. At 210 degrees, it hits the value of minus 0.5. So you can say that the sine of 210 degrees is minus 0.5. By the way, the sine of 210 degrees is equivalent to the sine of minus 150 degrees. It's the equivalent point. You can continue on and you find that the sine again hits minus 0.5 at 330 degrees, which is equivalent to minus 30. And carry that sine wave on beyond 360, making another rotation around the unit circle, you get to 570. I might have said 510 by mistake a minute ago. I meant 570, which is 360 degrees more than 210. And keep on going with your sine wave. You hit another point, 690 degrees, which is 330 plus 360. And it's also minus 30 plus twice 360, and so on. So every period of this sine wave, this from here to here, is described as a period, and there's a second period. Every period repeats itself, and so you pick up those same two solutions, but offset by 360 degrees, or some multiple of 360 degrees. Right, so conventionally though, you need to choose one solution because your pocket calculator, for example, will return a single value for inverse sine, inverse cos, inverse tan. And by convention, you choose the first and fourth quadrant for inverse sine, inverse tan, and you choose the first and second quadrant for inverse cosine. So you get one result in those quadrants for those functions. And then you'll need to look, at the unit circle to see where the equivalent result is in another quadrant. And you'll see two solutions in the unit circle. Once you have your two solutions, you can find more solutions by adding or subtracting any multiple of 360 degrees. And that's important, and that does come up in exam questions. We'll be looking at one of those questions later on. Okay. Let's move on now to compound angle formulae. These are four most important of them. So they're looking at cosine of some combination of angles, a sum or difference of two angles, or the sine of the sum or difference of two angles. And you do need to be able to derive these. You don't necessarily need to remember them because they are in the log tables. But you need to be aware they are in the log tables and what format they have, so that when a question comes up that you need to apply them, you know it's there and you know how to proceed. Now, from the point of view of deriving these formulae, the strategy is derive one of them first, and this is the one we derive first because it is easily derived using the cosine rule. And once you have this one proved, you can then prove these other three very easily using the negative angle and complementary angle formulas that we already derived. So let's start on the cosine A minus B identity. And we start with an angle A as before. Angle A, it's a positive angle A. So its intercept point is cosine A sine A. Then we add in an angle B. I've made this angle B a bit smaller here so that A minus B will be positive because we're looking for a formula for the cosine of A minus B. And then we draw them on the same circle, A and B here. And the angle between A and B is obviously A minus B. The angle between those two lines is A minus B. And you can see that those two lines will describe a triangle inside a unit circle. So we complete that triangle with this chord of length L. And we find that we have an isosceles triangle here, two lengths of length 1 because they're radii of the unit circle, and a chord of length L that we can determine later. Right, so how do we prove the compound angle formula? Well, we note that we have this unknown length L, but we can work out L from the coordinates of the two endpoints, cos A sine A, cos B sine B, using the normal distance rule from coordinate geometry, which is equivalent to the Pythagoras rule. So that's one way to calculate L. But we can also work out L using the cosine rule in terms of the cosine of this angle A minus B. And by working out those two ways and comparing, we can eliminate L and get a formula for cosine A minus B in terms of these other terms, cos A sine A, cos B sine B. Okay, so that's the strategy. The details of it are: apply the cosine rule. For this triangle, normal would be A squared equals B squared plus C squared minus 2BC cos A, where in this case, the A is the length L. The B and C are both 1 because the length of those two sides is 1. And the angle is actually A minus B here. And this is how the formula looks then. It's L squared plus 1 squared plus 1 squared minus twice 1 by 1 by the cos of the angle. The other expression for length L is, well, normally you'd have the square root of this quantity, but we're happy enough to stick with L squared rather than L because we have L squared in the other formula. So instead of the x2 minus x1 squared and y2 minus y1 squared, we substitute the known values of x1, y1, x2, y2, which are cos A sine A and cos B sine B. And we get this formula for L squared.
Apologies, Frank. I've got a question coming in from the audience there.
Sure.
About how can you use Pythagoras theorem if there is no 90-degree angle?
Okay, it's a good question. I've called it Pythagoras. You may, I don't know whether you have covered coordinate geometry yet, possibly not. The formula for the distance between 2 points is the square root of x2 minus x1 squared plus y2 minus y1 squared. That is derived from Pythagoras, and the way you would derive it is you would draw a line horizontally from this point over to here and a line vertically here, constructing a right angled triangle here. You could also do it down here. It's equivalent. Whichever way you do it, you have a horizontal line there whose length is the difference between x2 and x1. So it's x2 minus x1. And then the length of this vertical line would be y2 minus y1. So you have this right angled triangle here, and apply Pythagoras to that right angled triangle, you would get L squared is equal to this length squared plus this length squared. So I took a shortcut in not describing that. I probably should have drawn that in on top there. It is a result from coordinate geometry, which you, I'm not sure whether you had done that in the junior certificate or not. You will be doing it, if not in the leaving certificate. I think it is a junior certificate result, actually. But you can correct me if I'm wrong there. But this formula for the length of a line segment, where you know the X and Y coordinates, is one that you do need to remember. Ultimately, it is derived from Pythagoras, but you can just remember it in this form and ignore the fact that I've called it Pythagoras. Okay? Right, I'll move on there. So using those two previous results, the second result first, the L squared in terms of those coordinates, replacing the x1, y1, x2, y2 by cos A sine A, cos B sine B, you need to multiply it out. And you get a total of 6 terms when you multiply those, when you square that and you square that. Those are the 6 terms. And the important thing to notice is that you get a cos squared A and a sine squared A in there, which you can group together. You have a cos squared B and a sine squared B, which you group together here and leave the other 2 terms alone. And an identity that you do need to remember is that the cosine squared plus the sine squared of any angle adds up to 1. And you'll be using that identity over and over again. So that is an important one to remember. It is in the log tables. That one is so fundamental that you shouldn't even need to refer to the log tables for it. So replacing this cos squared plus sine squared by a 1 and that one also by a 1, you get to this formula for L squared, 2 minus 2 cos A cos B minus 2 sine A sine B. Now it's convenient actually to work with L squared over 2, we'll see later, and then you just divide that across by 2, get a 1 there, and 1 there, and 1 there. Now returning to the formula, the cosine rule formula, the L squared equals B squared plus C squared minus 2BC cos A. That simplifies to L squared is 2 minus 2 cos A minus B. And we're nearly there then, because we now have an expression that contains cosine A minus B. So we rearrange it to get cosine A minus B is equal to 1 minus L squared over 2. And of course we had L squared over 2 in terms of the cosines and sines up there. So we substitute that in here. And we find that the 1's cancel out and these signs become positive signs. And eventually we find that cosine A minus B is cos A cos B plus sine A sine B, which is the desired result. Okay, now that's the most difficult of the derivations. Everything else is simple after that. But this is a derivation you do need to be familiar with. It's in all the textbooks. In some of the textbooks, in a lot of them actually, they put this first angle in the second quadrant, so it looks a bit different, but it's exactly the same calculation. Right, now, the next thing is to prove the cosine A plus B formula, and that's simple, starting with cosine of A minus B, which we've just proved, this formula here. We need to get this to cosine A plus B, so replace the B with minus B. And you get this here. And the cosine B becomes cosine minus B. The sine of B here becomes sine of minus B. And that becomes cosine A plus B from here to here. The cosine of minus B, of course, is cosine of B. That's from the negative angle formulas. The sine of minus B is minus sine of B. So substituting those in, this remains at cosine A cosine B, but this changes to minus sine A sine B. Right, the next one we want to prove is that the sine of A plus B is this quantity over here. Now you can start with, again, with the cosine A minus B formula, but now you want to convert this to a sine, and for that you use the complementary angle formula that we showed before. Sine of x is the cosine of 90 degrees minus x. Right, so we would like the sine of A plus B. That's what we're looking for. Using this formula, that's equal to the cosine of 90 degrees minus A plus B. And regrouping terms there, that's the cosine of 90 degrees minus A minus B. And now we can apply the original cosine A minus B formula, the cosine of a difference in angles. And applying that, we say it's the cosine of the first angle times the cosine of the second angle plus the sine of the first angle times the sine of the second angle, where the first angle is 90 degrees minus A and the second angle is B in both cases. And then we again apply the complementary angle formula. The cosine of 90 degrees minus A is the sine of A, and the sine of 90 degrees minus A is the cosine of A. And that gives us the result that we were looking for, sine of A plus B. And then very simply substitute minus B for B to get the to convert this formula into a sine of A minus B formula. And again, when you substitute minus B for B, the cosine doesn't change, but the sine does change to a negative sign. So you end up with sine A cos B minus cos A sine B. And that's the fourth of those compound angle formulas. You can do the same with tan A plus B, tan A minus B. Tan is defined as sine over cosine of an angle. So sine of A plus B over cosine of A plus B. We have the formulas for that just worked out. So you write those down. We need to convert that into a simpler format. And the way to convert it ultimately into tans is to make sure that we have sine over cosine. So if we divide all four terms in this equation by this single term cos A cos B, we do it here, 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 and here. We're not changing the fraction at all, but you get this term, the cosine B's cancel, you get sine A over cosine A, you get a tan A. For this term, the cosine A's cancel, you get a sine B over cosine B, which is tan B. And this down here, both terms cancel, so you end up with a 1. And over here, you get a sine A over a cosine A, a sine B over a cosine B. So that's tan A times tan B. And finally, if you replace B by minus B, then tan of minus E is minus tan of B. So this formula changes to this formula where we've flipped the sign top and bottom. And those are the formulas, compound angles of tan A plus B and tan minus B, tan A minus B. Okay, moving along, double angle formula. Cosine of A plus B. We had this result before. So the cosine of 2A, this is a double angle formula, just set B equals A, and you get cos A minus sine A, which is cos squared A minus sine squared A. And you can stop there, actually. However, you can also change, you can simplify it further if you use this identity, cos squared A plus sine squared A equals 1. So as I said, this is the most important identity in trigonometry. So I've highlighted it in red here. You'll be using it over and over again. You can use that to replace cosine squared by 1 minus sine squared. And then you end up with 1 minus 2 sine squared A is an alternative version of cos 2A. We could also have replaced sine squared using this identity by 1 minus cosine squared, which would have given us 2 cosine squared minus 1 as an alternative version for cos 2A. And that is actually, it was an exam question a couple of years ago to do exactly that, a particularly easy exam question. We'll show that in a few minutes' time. Now, for the sine of 2A, we take the sine of A plus B and replace B with A. Same principle, you get sine A cos A plus cos A sine A, which is 2 sine A cosine A. You can go through the same process with tan of 2A. And you end up with 2 tan A over 1 minus tan squared A. There are multiple ways of doing that. You could have just used the original tan A plus B formula and substituted B equals A. That would also get you to this point. Half angle formulas, well, you can do that just by replacing 2A by X. And that will be, that begins becomes X over 2. And you get the half angle formulas here. For cos X is cos squared X over 2 minus sine squared X over 2. And this formula translates into sine X equals 2 sine X over 2 by cos X over 2. All of these are in your log tables, so you don't need to remember these compound angle formulas. Just remember that they exist and where to find them. Now, there are more formula in your log tables, and there are these 4 formulas down here, which are used to convert products of sines and cosines into sums of sines and cosines. You don't necessarily need to know the derivations of these, but if you did want to know how to do them, it's quite simply done by adding or subtracting pairs of these equations. So you can see if you add this identity, which we've proven before, to this identity, this term will cancel with this term, and you end up with twice cos A cos B. All right, so that's how you get this equation down here, by adding equation 4 and equation 5. If you subtracted them, then this term would cancel this term, and you get twice sine A sine B, which is this last equation down here. And so on for, adding these 2 equations or subtracting those 2 equations would give you these 2 formulae. But you probably don't need to know those. They're generally not covered in your textbook. But you do need to know that these four identities are in your log tables. You know how to find them and know how and be able to apply them in an exam question. Similarly, you can go from you can use those same four identities and manipulate them into this other form, which allows you to go from a sum of sines and cosines, sum or difference actually, to a product of sines and cosines. You don't need to know how to derive them necessarily, but these four equations down here, you need to know that they are in your log tables and know where to find them, know how to use them. And in fact, there is an exam question using a couple of these identities, and we'll cover that in a few minutes. Right. We can look at some other variants here, and this is an introduction actually to trigonometric identities. You can be asked to show various other identities. So you can be asked, for example, to show this formula down here. It's yet another way of describing cos 2a. So you use this as a starting point. This identity, cos 2a, is cos squared a minus sine squared a. This one is in your log table, and they ask you then to prove this identity. So the way you do it, as usual, there may be more than one way. There often is in these. But the simplest way in this case is to take the original identity, and you can see that you want to get to an equation or a term involving tans. So a good way to do that is by dividing the original sine squared by a cosine squared. Of course, you can't do that on its own. You can only divide by something that doesn't change the term. So you can divide by 1. So we're using this famous identity, cos squared plus sine squared equals 1 to do that. Replace the 1 by cos squared plus sine squared. And now when you divide in you divide the well, actually, sorry, you divide above and below now by cosine squared. So all four of these terms get divided by cosine squared. And the clue to do that is that you want a 1 here and a 1 here. So dividing by cosine squared a will give you a 1 here. Same here, you get a 1, which is what you're looking for in this formula. And when you do the same thing with the sine squared, it'll give you a tan squared here. And down below you get another tan squared. So that's the result that you were asked to find originally. We'll go through a bunch of these trigonometric identities now. There are several tricks that you need to become used to. So we'll work through a few of them just to get you familiar with them. Here's another identity you're asked to prove. Now, generally the strategy is you take the left side and try to make it into the right side. So use the form of the right side as a clue to how to get there. So in this case, you see that the right side only contains functions of a, whereas the left side contains functions of 2a. So you need to use formulae that convert these functions of 2a into functions of a, which is the double angle formula. Now in this case, you need to convert cosine of 2a. Now the other clue you should take is you're looking for tan or tan squared in this case. So to get a tan, you need a sine above the line and a cosine below the line. So the way you go about it is you replace the cosine of 2a by something that contains cosine of a, and you replace the cosine of 2a below the line by something that contains sine of a. So we go back to this identity that we proved before. The cosine of 2a is 1 minus 2 sine squared of a. That's a candidate for putting underneath the line. But you can change that using, again, cos squared plus sine squared equals 1 into this version of a cos 2a formula, which contains only cos a, and that's a candidate for going above the line. All right, so you take this identity and replace the cos 2a above the line, and you take this identity and replace the cos 2a below the line. And when you do that, fortunately, the ones cancel out nicely, and you end up with 2 sine squared a over 2 cosine squared a, which is a tan squared a. I apologize for going through this quite quickly, but time is short. I want to get on to a couple of exam questions. But you can look over these in your own time and give it a bit more time to see what's going on. Here's another trig identity. So you're asked to prove this. Again, look for a clue. You want to convert this format, the left-hand side, into this format. On the right-hand side, you see a half angle. So you use a half angle formula from your log table. So use a half angle formula for sine x, which is this. You see that in your log table. And you use the half angle formula for cosine x, which is this. Again, you find that in your log table. Do as much simplification as you can. The ones cancel out down here. And now you find that you have a cos x over 2 on top. You have a cos squared x over 2 on the bottom, so you can divide above and below by cos x over 2, leaving you with sine x over 2 on top, cos x over 2 on the bottom, which is your tan x over 2 that you were asked to prove. A third trig identity here. You're asked to show that this equals this. So we try to convert the left-hand side into the right-hand side. Again, the right-hand side only has a function of x in it, whereas the left-hand side has some functions of 2x. So you use the double angle formulas to get rid of the 2x. And when we do that, we see that the sine 2x gets replaced by 2 sine x cosine x. The cosine 2x, we want to replace it by one of the identities for cosine 2x. We saw several of them, but we would like to get cosine x below the line in order to get a tan x result. So we use this version of the cos 2x identity. And when you do that, you find we have a 3 sine x plus 2 sine x cosine x on top, which you can factorize, put out the sine x, and times 3 plus 2 cosine x. Similarly, you've got 3 cos x plus 2 cos squared x below the line, which you can factorize, take the cos x out, and 3 plus 2 cos x. And nicely, you get those second terms canceling, leaving you with sine x over cosine x. That's tan x is your result. Okay, we've got 10 minutes left, so quickly I'll run through a couple of exam questions. Again, I apologize for the speed here. 2016, question 3, there is a trig identity for you to solve. So it's the same procedure as before. We tried to get this equation in this format. The right-hand side contains 3a left-hand side contains 7a and a. If you look through the log tables, the only way you're going to get from 7a and a to 3a is using these formulas that contain a plus b over 2 and a minus b over 2, because 7a plus a over 2 will give you 4a, but 7a minus a over 2 will give you 3a. All right, so you use those sum and difference to product formula because you know they'll give you the 3a's that you want. And actually when you apply them, because the sums will give you a 4a, the differences will give you 3a, and you get 2 cos 4a cos 3a over 2 cos 4a sine 3a. And fortunately, the 4a terms cancel, leaving you with the 3a functions, which is cosine over sine is the cotangent of 3a. That was a relatively difficult identity, but it was an exam question, so it just shows you do need a lot of practice with these identities because you never know what will come up. Part B of that question is a little bit easier. They give you that cos 2 theta is 1 over 9, you want cos theta. So you use a formula, a double angle formula that converts between cos 2a and cos a. You start with the one that's in your log table, use the normal identity that sine squared plus cos squared equals 1, and you get this version of the identity. Cos 2a is 2 cos squared a minus 1. Replace a by theta, you get it in this form, and now you have an equation in cos squared theta, but you're told that cos 2 theta is 1 over 9. So you plug that in, and from then on it's just arithmetic. You eventually find that cos theta is plus or minus root 5 over 9. And you can take the 1 over 9 out of the square root to get root 5 over 3, which is the format they're looking for, the square root of an integer over another integer. Okay, 2018, they had an inverse trig problem in question 4. Find all the values of x for which cosine x 2x equals minus root 3 over 2. Now, at first glance, all you need to do is take the inverse cosine of minus root 3 over 2, and that's your solution. But remember before, you have to be careful that there are multiple solutions to that. And they gave a clue because they said all, and they put the word all in bold. So you need to watch out for things like that. They're looking for all of the values that satisfy that. So if we were to plot the cosine function, or alternatively just draw it on a unit circle, you'll see that this value of minus root 3 over 2, which is minus 0.866, will cut through the cosine wave somewhere in this second quadrant, and again somewhere in the third quadrant. Now, if you use your calculator and take the inverse cosine of 0.866, it'll give you 150 degrees. So you can draw that on the unit circle, but you need to observe that there is another point that has the same cosine in the third quadrant at 210 degrees. But you also need to know that you can add 360 degrees and get the same value of cosine again, and another 360 degrees will get you there again, and so on. Right, and then there are 4 solutions which are 150 degrees to, well, sorry, there are multiple solutions, but they ask you for solutions where x is between 0 and 360 degrees. But if x is between 0 and 360, then 2x is between 0 and 720. So you only need to look at the solutions between 0 and 720. Those are their 4 valid solutions: 150, 210, 510, 570. But those are for 2x, right? So there's a trick in the question. That's 2x, these values. The actual answers are for x. So cut those, or divide those by 2, and those are your 4 solutions. To do it more formally, you say, okay, from the unit circle, we see we have 150 degrees and 210 degrees as our solutions. You can add any multiple of 360, so n times 360, to either of those solutions. For 2x, for x, you need to divide, so the solution is 75 plus n times 180, or 105 times n times 180. And these generally, there'll be 75, 255, 435, and so on, adding 180, or 105, 285, 465, and so on, adding 180. But you only take solutions between 0 and 360 degrees, and only the first 2 solutions here are in that range, and only the first 2 solutions there are in that range. So you take those four answers. Okay. Part B, just quickly, they're giving you cos A is y over 2. They ask for sine 2a. Now, in the model answers, they have quite an elegant geometric solution drawn there. That wouldn't necessarily, it wouldn't occur to me if I was doing it in an exam. So I'm showing you a brute force solution here, where you simply write sine 2a in terms of y. Well, just use the compound angle formulas to express sine 2a in terms of y, which is a function of cosine a. So sine squared 2a is the, you want to change between sine 2a and cos 2a. So you use the fact that cos squared plus sine squared of an angle is 1. So sine squared 2a is 1 minus cos squared 2a. And then replace the cosine squared 2a. Replace the cosine of 2a by the 2 cosine squared a minus 1 compound angle formula. And you have to square that to get it to cos squared a. And now you're in a position to replace the cosine of a by y over 2, which is what you were given in the formula. You have to do a bit of arithmetic, and eventually you find that sine squared of 2a is this term. So the sine of 2a, which is what you're looking for, is the square root of that. Pull the 1/4 y squared out of the square root, and you get this solution. Okay, and very quickly, 2019, there's a very simple identity to show there. Take this from your log tables, the cos 2 theta is cos squared minus sine squared, and use cos squared plus sine squared equals 1 to replace the cosine squared by 1 minus sine squared, and you get your desired result. Right, and the very last question then is part B of that same question. They ask you to find the angle between 2 internal diagonals of a cube. And to do that, I've drawn in some dimensions. Assume that the cube is of edge length x. First, work out the length of one of the face diagonals, which I've called d here, and it's simply given by Pythagoras. So d squared is twice x squared. And then if you observe this triangle here with D being one of the lengths, this edge X being a second one, and this internal diagonal being a third. That's a right angle triangle there. So you can work out the length of this internal diagonal using Pythagoras. I'm calling that length L here, and that length squared is this D squared plus X squared, which turns out to be 3X squared. So the length of this internal diagonal turns out to be √3 times the length of an edge. We're interested in the length Y, which is half of that. And now you're in a position, you have this triangle here, which contains the angle that you're trying to find. And you know this length Y. This other half diagonal is also of length Y, and you know the length X. So you can apply the cosine rule. So x squared, y squared plus y squared minus 2y squared cos theta. Replace y by this, and now you get an equation in all x's, and ultimately the x's cancel, and you got cos theta is 1/3. Okay, so that's relatively simple trigonometry. It just was a little bit difficult to visualize where all of these right angle triangles were to do it. Okay, we're 1 minute over, so I'll end there unless anyone has any questions, and I'll hand back to Eamon there. Thank you.
Thank you, Frank, for a very nice presentation and for doing several examples there in trigonometry.
And I would encourage lots of practice on trig identities, because as you see there's a bit of guesswork involved in how to go about solving any particular identity.
Yes, and I think that's very important for maths in general. You've got to practice the questions, past papers and books, examples, everything you can find really. Just keep practicing, because if you practice, they'll become more familiar and you'll get better and life will be easier. Okay, well, for now, I think we're going to finish up here. We've gone slightly over time. We had some internet glitches, but we got everything covered. I'd just like to, before we go, say that definitely practice what you've seen here today. Get some questions and do some practice. Very useful are the formula and tables booklet. So don't leave it until the morning of the leaving cert before having a good look at this booklet. Use it now when you're doing questions and problems, and you get used to knowing where to look. There's more than 90 pages in this booklet, so you don't want to be trying to figure out where things are at the last minute. So use that a lot now, and it will make life much. For all subjects for this, there's stuff in there for physics and chemistry, and also there's lots of new things in there for financial maths. So very useful. Also mentioned in today's tutorial was the khanacademy.org, and that's all for now. We'll see you next week for the geometry of the line tutorial. Okay, so bye for now.